Okay, I'm going to talk about moles and chemical formulas. So first, let's start with the mole. So you need to know what a mole is. It's a quantity we use in chemistry a lot to quantify amounts of substances. And a mole is simply equal to 6.022 times 10 to the 23rd, which is actually called Avogadro's number. You can actually get more sig figs. You can look up, we know it to a greater accuracy, but typically we'll use it to four significant figures. So the 6.022 times 10 to the 23rd. When we use this as a unit quantifying an amount of something, we abbreviate it just as MOL. You know, that doesn't seem like it's helping a lot, but you can't abbreviate it just as M because just the letter M is actually already multiple other units. So the letter M is meters. The letter M is also molality. So moles is abbreviated as MOL. You can't shorten it any more than that. Now, this actually is the number of carbon atoms in exactly 12 grams of carbon 12. That's where that number comes from. And so that is just kind of the foundation of it. But we use this as a clustering number, essentially, a counting number. It's similar to a dozen, okay? It's just a much larger grouping number. And so, you know, when we have a dozen of something, everyone knows that's 12, whatever you're talking about. So a dozen eggs is 12 eggs, a dozen donuts is 12 donuts. Or you could say you have 2 dozen of something, like 2 dozen eggs, and everyone knows that's 24 eggs, right? But that's a simple conversion that there's, for every 1 dozen, there's 12 of something. Right? This is the same thing. For every 1 mole, there's Avogadro's number of that thing. So we could apply it to anything. And so you could apply it to eggs and donuts if you wanted. It's kind of silly because we couldn't possibly have that many eggs or donuts. But you could say 1 mole of eggs is 6.022 times 10 to the 23rd eggs. Okay, or 1 mole of donuts is 6.022 times 10 to the 23rd donuts. But again, like I said, that's kind of silly. We don't use that type of, or that large of a grouping number for macroscopic objects because we're not going to have that many. But when we're dealing with atoms and molecules and ions, things like that, we do have sample sizes on the order of moles. And so we use this as our clustering number. So you could apply this to different types of atoms, ions, molecules, and ionic compounds, so formula units. So some examples, a mole of hydrogen atoms would be 6.022 times 10 to the 23rd hydrogen atoms. A mole of water, or H2O, would be 6.022 times 10 to the 23rd water molecules. A mole of Na plus would be 6.022 times 10 to the 23rd Na plus ions. Mole of NaCl would be 6.022 times 10 to the 23rd NaCl formula units. Okay, now notice that the unit of that value changes. And so H is an atom, so it's hydrogen atoms or atoms of hydrogen, if you want to say it that way. And then H2O is a molecule, and so it's the number of molecules. Na plus is an ion, so we use the unit ion. NaCl is an ionic compound, which comes in units of formula units, okay, not molecules. And so all of those things are just telling you what 1 mole of something would be, okay, but it's always Avogadro's number of whatever that thing is, okay, whether it is a molecule, an atom, an ion, and so on. And we use this as a conversion factor. Okay, so we utilize this in dimensional analysis. So we can set up ratios of this information. Since these things are equal, you can put them in a ratio and you can multiply them in any dimensional analysis to convert units. Now, of course, you would do this to convert between one, you know, those units that are in that in that relationship. You wouldn't just randomly do it. But if you wanted to convert between, say, hydrogen atoms and moles of hydrogen, whether you're going from moles to the number of hydrogen atoms or from hydrogen atoms to the number of moles, you're going to use a different ratio, whether, which way it's flipped. So here's your two possibilities for that scenario. So we've got either 1 mole of hydrogen, okay, over 6.022 times 10 to the 23rd hydrogen atoms, or 6.022 times 10 to the 23rd hydrogen atoms over 1 mole of hydrogen. Okay, so you can multiply by either of those ratios, and you're not actually changing what you have because you're multiplying by 1. You're just converting the unit. Okay, so you should be converting between atoms and moles using those ratios. Okay, so let's look at some examples of using Avogadro's number to convert between moles and whatever particle we're talking about. Okay, and so I guess before I have the examples, I want to show you the basic layout. So conversions using Avogadro's number are always going to involve moles of something and particles of that same something. Okay, so the basic idea, we have moles of A, and we can convert it to particles of A. Or we could take particles of A and we can convert it to moles of A. Okay, so that particles part, I'm using a generic term because A could be an atom, a molecule, an ion, a formula unit. It doesn't matter. The setup is going to be the same. Okay, so if, for instance, we were going from moles to particles, then you would start with moles given. Okay, that's what I have listed first. So here, that box would be where you put the number of moles of that substance that you're given. And then you would multiply by a ratio to cancel the moles and give you the particles. And so I put moles opposite. So I put moles on the bottom because really, remember this, when I have just this standalone number, it's really that over 1, right? So if I put moles on the bottom and particles on top, then my moles part is going to cancel, okay? And for 1 mole of anything, there's Avogadro's number of particles, okay? And so then you would multiply that through and you would get the number of particles of that substance. That would be your answer if you're just trying to do that one conversion, okay? And you can do this in the reverse, okay? You can go from particles to moles. So if you were given how many particles, so how many atoms of something or how many molecules of something, then you would start with that value, okay? And again, that value is really that over 1, okay? And so then if you want to convert those particles to the number of moles, then you would put particles opposite so that the particles cancel, and you put moles on top. And 1 always goes with the moles, and 6.022 times 10 to the 23rd always goes with whatever particle it is that you're dealing with. And so you would multiply through, so you would take your value and actually divide by Avogadro's number, and that would give you the number of moles of whatever you're looking for. Okay, so that's the basic setup, but now let's apply that to some examples. So, oh yeah, I guess I did have one more note here. Particles can represent any type of matter, including atoms, ions, molecules, formula units. Those are the things really that we deal with in chemistry, or pretty much those 4 things, but you could apply it to anything you could think of. But again, we'd really only do this on a microscopic level. So when we're talking about things that are tiny, you wouldn't apply it to things like donuts and eggs and cars and people, because there's not that many of those things. Okay, so on to the examples. So some mole calculation examples. We just do these simple 1-step calculations. And as we build and learn more types of conversions, we'll start looking at more complex ones. But for this video, we'll focus on just using Avogadro's number. So this first one, I say, how many atoms are contained in 2.15 moles of magnesium? So we're only given kind of one piece of information and we're looking for one thing, right? We're given moles, we're looking for atoms. And so I'm going to start with what's given. So that would be the 2.15 moles of magnesium. And I'll write moles as MOL, the unit, and magnesium as Mg. Okay. And that I want to get rid of moles. So remember, this is really over 1. I want to get rid of moles. So I'm going to put moles on bottom. Moles of magnesium on the bottom. And I want atoms. Okay, so I want atoms of magnesium. And then I'm going to fill in my numbers. So I've got my units set up to where I'm going to cancel what I don't want. I'm going to get what I do want. And you should know that 1 mole of something contains Avogadro's number of whatever that is. So 6.022 times 10 to the 23rd of that thing. Okay, so that's going to cancel my moles. It's going to give me atoms. So now I just need to type it into my calculator. Now you've got to be able to type scientific notation into your calculator. You can use all kinds of parentheses and such. It's much easier if you know how to use the scientific notation button. And so if you have an EE or an EXP button on your calculator, if you type 6.022 and then hit that EE or that EXP button, it should bring up either exponents or it'll just show an E. And right after that, you type 23, and that E part is the times 10. Okay. And then that's much easier and quicker than trying to, go in and do times 10 and use a superscript. And then having to use parentheses when you're trying to divide. You don't have to do that if you use the scientific notation button. It's much quicker. Now, the answer, I'm going to round to 3 significant figures because the starting value is 3 significant figures. Okay, and Avogadro's number, as we're using it, is 4. So 1.29 times 10 to the 24th atoms of magnesium is what I get. And that's not a very good M, but we'll call it good enough. There we go. Okay, so that's one example. Let's look at another one. Now here I say calculate the number of molecules contained in 6.75 moles of dinitrogen monoxide. Okay, so again, I'm going to start with what's given, the 6.75 moles, so MOL, N2O. And again, if it helps you, you can write that over 1. And I want to get rid of moles of N2O. So I want to write that opposite so it cancels. And I want to go to molecules. And there's not really an abbreviation for molecules. Be careful if you abbreviate things that it doesn't overlap with something else. Okay, so now we can fill in our information. For every 1 mole of something, there's Avogadro's number of that thing. Okay, so 6.022 times 10 to the 23rd molecules in 1 mole. So the moles portion cancels, and it's going to give me the number of molecules. So I take 6.75, I multiply by 6.022 to the 23rd. Okay. And that, again, I'm going to round to 3 sig figs because the 6.75 is 3 sig figs. So that would be 4.06 times 10 to the 24th molecules of N2O. And that's my answer there. Okay, let's do one more. So here I say calculate the number of moles that contains 3.15 times 10 to the 25th formula units of FeO. Okay, now I know a lot of times people will see formula units and they'll throw them off and they'll say, I have no idea what to do. Well, a formula unit, remember, is just the individual unit of an ionic compound. So it's the smallest ratio of ions. that combine to make a neutral unit. Okay, so it's similar to using the term molecule, okay, but it's the proper term to talk about ionic compounds. So I'm going to start with that, the 3.15 times 10 to the 25th formula units. And again, there's not really an abbreviation for this either. And so that I want to cancel the formula units. So I'm going to put formula units on the bottom. Maybe formula units, and I'll do form unit easier FeO, and then moles of FeO on top. And 1 mole of anything is 6.022 times 10 to the 23rd of that thing. Okay. So let's see. Oops. No. Slide quite yet. Let's do this. There we go. So 3.15 times 10 to the 25th. And then I need to divide by Avogadro's number. So if you're going to manually type it in and not use the scientific notation button, you need to put it in parentheses if you're dividing by it. But if you use that scientific notation button, the EE or EXP, you can just hit divide and then do 6.022, hit your EE or EXP button, and then hit 23. And that gives me 52.3. And again, this one started with 3 sig fig number, and that would be moles of FeO. So that would be my answer for that. Okay, so hopefully that gives you an idea of how you can go about doing conversions between moles and whatever particle you have. And so you always use Avogadro's number. It's just depending on which direction you're going will determine whether or not you're multiplying or dividing. And I would recommend not trying to memorize that because then you risk, getting it backwards. So if you just follow the units and you use dimensional analysis, it will force you to multiply or divide as needed. Okay, so let's look at more. I'm going to talk a little bit about chemical formulas. Because you can also build conversion factors out of chemical formulas, because really a chemical formula tells you the ratio of atoms or ions in a compound. Okay? And so you can utilize the information in a chemical formula to determine how many total atoms you have in a sample, or how many ions you have in a sample, or how many of a particular atom you have, or how many of a particular ion you have in a sample of some compound. Or you can go the other direction. You could say, if I have this many atoms, how many molecules do I have? Or if I have this many ions, how many of the formula units do I have? So you have to be able to look at a chemical formula and determine what's the ratio. You have to be able to kind of write that ratio, that relationship. So I've got some examples. So if we have NaCl, hopefully it should be obvious when you look at that chemical formula that one formula unit of NaCl is actually one Na plus ion and one Cl minus ion, right? That's why there's no subscripts there, because there's one of each in a formula unit. You can also talk about this ratio in terms of moles instead of those individual particles, okay? Because if you have one formula unit, and that's one of each ion, then if you had 1 mole, then you should have 1 mole of each of those ions, okay? Because we're just scaling it up by Avogadro's number, okay? We're essentially multiplying each of those things by Avogadro's number. And so it's actually the same ratio in the end. It's just on a scale that's a little more useful to us, because we don't work with samples of individual atoms or individual ions, right? We work with larger samples that contain things on the order of a mole of things. And so the other examples I have here, I have CO2, so carbon dioxide. So if you had a molecule of carbon dioxide, if you look at that chemical formula, you should see that for every one CO2 molecule, you have one carbon atom and two oxygen atoms. Okay, but more usefully, we can talk about it in the terms of moles. And so 1 mole of CO2 would have 1 mole of carbon atoms and 2 moles of oxygen atoms. And then lastly, I've got another ionic compound here. I have manganese 2 nitride, so Mn3N2. So one formula unit of that contains 3 manganese 2 plus ions and 2 nitride ions. Whereas, again, you can talk about it in terms of moles. So 1 mole of Mn3N2 would contain 3 moles of Mn2 plus and 2 moles of N3 minus. Okay, so all of that information you can get from the chemical formula, meaning there's a lot of different conversion factors using chemical formulas because there's tons and tons of different chemicals, right? Lots of different types of compounds. So you're going to use these for whatever sample you have. Of course, you're not just going to pick some random conversion that applies to some other molecule. It has to apply to your sample. So based on the chemical formula, your compound that you're dealing with, you can build ratios that relate the compound to the individual components, or even one component to another. So from all of this information, I've written a few ratios. Okay, now I haven't written all of the possible ratios that you could, but to give you an idea, so we can write 1 mole of Na plus over 1 mole of NaCl, or 1 mole of Cl minus over 1 mole of NaCl. Okay, or you can flip those, and you can use those then to convert either from moles of NaCl to moles of Na plus, or moles of NaCl to moles of Cl minus, or the other direction, moles of Na plus to moles of NaCl. So, okay, just like with the carbon dioxide, you can convert between moles of CO2 and moles of carbon, or moles of CO2 and moles of oxygen. Okay? And the same with that manganese 2 nitride. You can convert between the formula units and the individual ions. Meaning if you know how many molecules of something you have, or you know how many formula units you have, you can use that quantity and use the chemical formula to calculate how many of the individual units are in there. So if you split up the molecules, how much stuff would you have? Or if you split up the formula units or the crystal lattice of that structure, how many ions would you have? Okay, so that's kind of a useful conversion factor or piece of information that a lot of times people overlook because they think the chemical formula is only important just telling me what I have, but it can actually help you do some calculations. So that's helpful to you as well.